In this video, we are going to learn how results differ between a one-shot version and a repeated version of a prisoner's dilemma. Let us consider an advertising game between RJR and Philip Morris. Each firm has two possible actions, A, that is advertise, and DNA, that is do not advertise. We begin by considering a one-shot version of this game. The Nash equilibrium of this game is for both firms to advertise. Therefore, in equilibrium, each firm earns 100. However, if both firms had not advertised, each would have earned 120. Clearly, if no one advertises, each firm is better off, and yet the firms are unable to enjoy the superior outcome. This problem is known as prisoner's dilemma and occurs quite commonly in the real world. What prevents the firms from earning 120 each period? To answer this question, consider a thought experiment. Suppose PM realizes that the equilibrium output of 100 hurts every player, and to fix this problem, they offered to stop advertising if RGR also reciprocates. Given this offer, RGR will reason that they will earn 120 if they reciprocate, but more importantly, they will do even better and earn 150 if they continue to advertise. So even if PM makes such an offer, RGR will not reciprocate and PM will earn only 70 instead of the 120 it was hoping to earn. Knowing this, PM will never make such an offer in the first place and the firms will earn 100 each period. The reason why PM's offer fails to change the outcome is because of the one-shot interaction. RGR has no incentive to stop advertising in response to PM's offer because they know that in a one-shot game, PM will have no opportunity to retaliate. When we allow for multiple periods in the game, PM will have an opportunity to retaliate in future periods. Can we therefore conclude that the firms will earn 120 each period if we merely allow them to interact multiple times? We now consider this question. Suppose the payoff matrix per period remains the same, but the game is now played twice. We want to know if there are reasons to believe that the firms will refrain from advertising in some of the periods. Since there are multiple periods involved, we must use the logic of backward induction to solve this game. Backward induction means that if there are multiple periods in a game, we first analyze the last period followed by the second last period and so on. Let us therefore determine the equilibrium in period 2. Suppose period 1 is over and the firms are thinking about their actions in period 2. It means that there is one more period to go. Also, period 1 is in the past and can be considered as irrelevant. Hence, it is as if the firms are playing a one-shot simultaneous move game in period 2. Therefore, we can conclude that in period 2, the outcome will be same as in a one-shot simultaneous move game. That is, each firm will advertise and earn 100. The result does not depend in any way on the outcome in period 1. Now consider the relevant payoff matrix in period 1. The relevant payoff matrix shows the total amount each firm will earn over periods 1 and 2, given a pair of actions in period 1. For example, suppose each firm advertises in period 1. In that case, each firm earns 100 in period 1. We now add the payoff of period 2. But we argued that each firm will earn 100 in period 2, regardless of the outcome in period 1. Hence, if both firms advertise in period 1, each will earn a total of 200. Following this logic, the relevant payoff matrix in period 1 is determined by adding 100 to each payoff in a one-shot game. In this matrix, I added the subscript 1 to actions to indicate that I am referring to period 1 actions. The equilibrium outcome is for both firms to advertise in period 1. Will the result necessarily change if we allow for more periods in the game? The answer is no. Suppose there are 100 periods in the game. Let us first consider period 100. The payoff matrix in this period is same as the one we had in the one-shot game. Hence, in period 100, everyone will advertise. In period 99, the payoff matrix will be same as what we had in the first period of a two-period repeated game. Therefore, we can conclude that everyone will advertise in period 99. Hence, we know that every firm will earn a total of 200 over the last two periods, regardless of what happened till period 98. The relevant payoff matrix in period 98 can be constructed by adding 200 to each payoff in a one-shot game. Therefore, the equilibrium in period 98 is for each firm to advertise. Continuing with this logic, we can argue that each firm will advertise every period. So we will not find any change in the outcome merely by considering more periods in the game. I will now show that there is one situation when a repeated game changes the outcome in a prisoner's dilemma. This change occurs if it is the case that the number of periods in the game is unknown, that is, cannot be predicted in advance. Assume that each period it is known that the probability of the game continuing for one more period is P, where P is a number between 0 and 1. Think of 1 minus P as the probability of one of the firms going out of business next period. The probability of the game continuing for 2 more periods is P squared, for 3 more periods is P cubed, and so on. We will fix a strategy of PM, then we will find out if it is in Audger's interest to refrain from advertising each period given PM strategy. Suppose PM follows the strategy shown in the screen. This strategy is known as the Grimm trigger strategy. It says that PM will not be the first one to advertise. PM will also not advertise in any period as long as Audger has a perfect record of never having advertised in the past. If Audger ever advertised any time in the past, PM will retaliate by advertising every period. This strategy imposes the maximum punishment on PM if it does not reciprocate Audger's gesture of not advertising. If this strategy fails to induce Audger from stopping advertising, nothing else will work. And we can conclude that the firms will continue to advertise every period. Suppose RGR decides not to advertise any period. Given PM strategy, it earns 120 every period this game is played. Therefore, the expected payoff of RGR by not advertising is given by the expression shown on the screen. This expression is an infinite geometric series and can be simplified to 120 times 1 over 1 minus P. Now suppose RGR decides to advertise in period 1. In that case, it will earn 150 in period 1 and 100 from period 2 onwards. Therefore, RGR's expected payoff from advertising is given by the expression in the screen. By comparing RGR's expected payoffs from advertising and not advertising, we conclude that RGR will not advertise if P is greater than 0.6. Let us summarize what we found. We found that if PM follows the Grimm-Krueger strategy and the chance of the game continuing for one more period is greater than 60%, then RGR never advertises. Because of symmetry, the same conclusion will hold if we switch the words RGR and PM. Hence, we conclude that firms will never advertise if each firm plays the Grimm-Krueger strategy and if the chance of the game continuing for one more period is greater than 60%. This means that if both firms are financially healthy, such that the chance of bankruptcy is sufficiently small, it is possible for the firms to stop advertising and earn 120 every period.